Any questions? Is it on? Any questions from last time?
What is island in island?
What is that? Sorry?
What is island in the islands?
That we'll see today. So yeah. Well, at least the qualitative outline of the story. So I mean, there are many things to say. So we are kind of now we are in the the modern, all the new things. So which means the lecture will be more like a seminar, more like an outline. The last couple of lectures. But I think the things that you can go look up are not that difficult. Okay, so any other questions? All right. Looks like the chalks have improved. Great. Let's see. So so we are heading towards this island paradigm or whatever. So yeah, so first I wanted to define what this quantum extremal surfaces were, right? I did not really do that last time. So let's start with that. So let me first do it in the setting of IISc where things are more precise. Okay, so in IISc, so it's essentially a correction to the Ryu-Takenagi formula. So the idea is that, so we had, if you like, the Ryu-Takenagi, at least some version of the Ryu-Takenagi formula could be viewed as the statement that your okay, so this is the Ryu-Takenagi formula, if you like, which basically tells you what so let's say that, so you have, let's draw the standard picture. So this is some boundary region, well, let me call this X actually. So these 2 points are the boundaries of X, if you like. Okay. So so how should I write it? So this is, let me just look at my formula. Yeah, so let me fix the notation. So I'll call this chi, and these 2 points are the well, I mean, this is basically the boundary of chi, if you like. Sorry, these 2 points are the boundaries of chi. Did I screw up the notation? No. So this is area of X will be area of chi, and then the claim is that this region here, which let me call it some notation I need. So this is A. The boundary of A is also the boundary of chi. Okay. So, and this is the entanglement and entropy of, I don't like the notation A, but unfortunately I have kind of run out of stuff, so I'll just call it A. Okay. So this is the entanglement entropy of some subregion in the boundary of the CFT given some state. Okay. So this is for some state, and the state presumably has some IISc bulk description, and the idea is that you do compute these two things. Okay, so because there is a time direction, you have to extremize first, and then you look for the minimal one. Okay, so this is the prescription. So if it is time independent, space-time, etc., it really doesn't matter so much whether, like initially in the original Ryu-Takenagi, they just looked at a spatial slice. It was in Euclidean IISc. Okay, so things were much more simpler, but people have slowly, expanded it to various time-dependent settings. And with one version of Ryu-Takenagi that one could write is to say that the entanglement entropy of a subregion in A of some state, we haven't specified the state yet, but corresponding to whatever state in the CFT, the idea is that you will have some state in the bulk, okay, the gravitational state, and that will be some black hole or something like that, and then you compute this, and then you find this. So the generalized entropy, all it is really doing is that it basically adds a piece of this kind. I think I mentioned crudely what it was. Yeah, so this region here is, my notation keeps changing. Let me call this X, okay? this is x. This is sigma of x, and this I guess I'll have to use a. And the boundary of x is basically this guy here, and this is the same thing as the boundary of a. Okay, so sigma of x is the spatial region here on some Cauchy slice. So, yeah, so this is basically, these two are, this surface and this surface are codimension 2 and this is codimension 1. And this is some spatial slice. And the prescription is that you extremize this thing. And note that this is a bulk field living in the space-time, in the gravitational space-time. And the idea is that in principle you should also include gravitons, even though, I mean, people say various words, but in most cases you're not able to compute it. That's the reality of it. So, but, at least in the cases that we will want, there are some, I would say not completely watertight, but reasonable claims about how this object behaves. And yeah, so some of these, so as I said, we are in the kind of the seminar phase of the final stages of this course, which means that like some of these calculations, I mean, like I can tell you the papers, and you can go look at them if you want. I'll just tell you the story in the next couple of lectures. So yes, so this is the prescription, and this is what we want to compute. So if you extremize it, you might find multiple surfaces. So then you pick the one with the lowest one. So that's what min means there. Okay, so you extremize it, this quantity, you extremize it by varying this x. X is the object that you're varying. So with a fixed boundary, which is dou x, or which is the same thing as the boundary of A. X is QES. Yeah. X is the quantum extremal surface. The quantum extremal surface is codimension 2. So, and that thing you vary, and then the claim is that you find this quantity. So a couple of statements, which is that one of them is that, see this this is a calculation which you're supposed to do in bulk effective field theory. But the answer you're getting is something in the CFT. Okay? So this is supposed to be a fine-grained result. This is supposed to be a, given some state, this is its genuine von Neumann entropy. So in this picture, dx is the same thing as dA. So I'm anchoring my extremal surface to the boundaries of the boundary subregion.
D sigma x.
What is d sigma x? D sigma x is x and A. Yeah. So that's, I have not emphasized it, but that's part of the prescription for this, which is that it's supposed to satisfy a homology condition, which means that the boundary of sigma x should in fact, should be x minus A. So homology, I didn't want to introduce it because homology involves, some choice of signs. So it should be defined in such a way that it's somehow x minus A. So that's the idea. But roughly speaking, it should be sort of, yeah, I mean, there are places where you will have horizons, and then, let's say, let me look at a spatial slice of a geometry with a black hole. Okay, and I'm computing Ryuta stuff. So, and then you can have scenarios where, so here the assumption is that I'm working with a mixed state. Okay, I'm computing it for a mixed state, and let's say you have some subregion like this. So this is your RT surface, and as the size increases, you can get to a place where the minimal guy would be something that is, something that contains a piece which is like this. So let me so this is one stage of the RT. So if you have a subregion which is like this, you could have something like this. Then you could have another one where you have sort of, you may have this, but you may also have one of this, and then this plus this may happen to be smaller than this one, in which case that's the correct RT surface. So there might be some horizon containing RT surfaces, but the key point is that because of the signs with which we are defining this homology, this is still in the sum of these two is still in the homology class that is of the boundary subregion. Okay. Central piece is the horizon. So, and assuming that you are computing it in a thermal state. So we will generally not be interested in computing the RT surfaces and RT surfaces or quantum extremal surfaces in thermal states. We will be interested in actually at least guessing what they are in pure states. Okay, so very roughly speaking. So our quantum extremal surfaces will be able to penetrate the horizon today. So generally, but if you are looking at this as a thermal state, this is part of the entropy that it will count, etc., etc., and this is the standard RT calculation that Ryu and Takenagi did in their original paper. Okay, so yeah. So yeah, so that's an illustration of the homology constraint on the RT surface. But anyway, so that doesn't matter for us actually today. So what is T of x?
Sigma is T of x.
Sigma, no. So that is, this is extremization, sorry. Extremizing over the x. So you first extremize over the x. So as I was saying that in extremization as opposed to minimization is necessary because you're working in Lorentzian signature. So sometimes it's called a minimax or maximin prescription. So you sort of, roughly speaking, you minimize on the spatial slice but maximize on the time slice. So yeah, I'm just going to tell you kind of a fairy tale version of the story today anyway. So it's kind of like how our ADS-CFT was. The first lecture on ADS-CFT. So yeah, so some things like that. So the point is that the bulk, so the surprising thing or the interesting thing about this is that this is a calculation that your instructor do in bulk effective field theory. In fact, that's somehow the most interesting thing about the Ryu-Takenagi formula. Because Ryu-Takenagi formula is in bulk effective field theory, its origins are somehow mysterious. So even when you try to, even in attempts to connect or sort of derive ADS-CFT, what people typically do is you start with some limit of the conformal field theory in the large N limit where the couplings are weak, etc. And then they are able to sort of perturbatively derive string theory. Which you can rewrite this perturbation expansion of the gauge theory as a perturbative expansion of the string theory. But bulk effective field theory is somehow conceptually a different beast. And this is oftentimes not emphasized, but I think that's a very striking fact about ADS-CFT. Because bulk effective field theory, its origins are somewhat mysterious. You know what I'm saying? How did it's somehow the low energy limit of the full string theory or the full n equal for superangles in the limit when in some low energy and effective field theory limit, but I don't think we fully understand, especially around black hole backgrounds, what limit corresponds to a fixed geometry, fixed space-time. I don't think we fully understand that, okay? So, but on the other hand, perturbative string theory, there has been progress. I mean, there are papers by, Rajesh and his collaborators and so on, even recently. I mean, the progress has been sort of steady. That you can rewrite. So the old idea of Toft is basically that you can write large N gauge theory perturbation series. You can rewrite it as a string theory. So so this is essentially the idea that if you have a Feynman diagrams, the Feynman diagrams basically get organized in counting genuses, genus of the Riemann surface on which you can write the Feynman diagram. Do you understand that statement? Is that clear, or is there anybody who's perplexed by it? I think the statement is correct. So essentially what I'm saying is that you can on this torus, for instance, you can triangulate this surface using Feynman diagrams, right? And there is a sense any surface you can triangulate it using Feynman diagrams of whatever kind. It's roughly So there is a question of whether Feynman diagrams are duals, etc. So let me not get into that. But roughly that is true. Okay, so but the point is that so the idea is that if you organize your Feynman diagrams in a large N gauge theory, they are automatically nicely organized in terms of genuses on which these Feynman diagrams can be written. So Toft's conjecture or speculation or the hope/dream in some sense was that in some large N in some large N limit, it should be possible to really fill these holes in the Feynman diagrams and really interpret them as Riemann surfaces, in which case it is a string theory perturbation expansion. So that picture has always been around ever since, actually Toft's paper is about only 2 or 3 years after asymptotic freedom was discovered and people realized that QCD is the correct theory. So it's like, it's shockingly fast that he realized that large N is a good approximation. So the point is that in that expansion, you can, it is natural to think that string perturbation theory can be understood in terms of large N perturbation expansion. But the point in some sense is that it's not clear how one gets bulk effective field theory. Because bulk effective field theory is something that is more mysterious because it involves dynamical gravity in some background and not perturbative strings around the same background. Okay, so that is a more confusing thing, but generally speaking, people believe that in some string theory, in its low energy limit, gravity emerges, and these are the solutions of that, etc., etc. So that picture is so Ryu-Takenagi is one of the few formulas that we have where it seems like the CFT quantities directly seem to connect. Some fine-grained CFT quantity directly seems to make connection with bulk effective field theory. This is usually not the case in many of the, well, I mean, yeah, at least in the specific sense that I mean, it's not really, bulk effective field theory is not so easily accessible. In the structure of bulk effective field theory is not that accessible in this language. So that's what this is doing. Okay, so this is our bulk. So this is a bulk field theory calculation in which you hope that you can compute various entanglement entropies of these fields. And also I should emphasize that this doesn't even have to be a perturbation theory or anything like that. It can be any, so this is a perturbation expansion. So this is assumed to contain all order corrections in G Newton. Okay, and this is 1 by G Newton. Note that this is, naively, this is a massive correction. So if you're looking at a fixed background and you're looking at thermodynamic entropy or some entropy, that's order G Newton or higher. That's roughly what bulk effective field theory contribute. So what really Bekenstein did was the opposite of a small correction. So this is a huge correction. You know what I'm saying? This is 1 by G Newton, which is huge. So this is the thing that is genuinely thermodynamically well defined. It was his observation. And so so this is supposed to be true all orders, but at the same time that's a statement about perturbative G Newton coupling. It doesn't say anything about what the other couplings in the field theory are. So this could be a strongly coupled field theory living in the bulk like UCD. It's still perfectly, this entanglement entropy, as long as it's well defined, this is a valid formula. If you can calculate it, you have the power to calculate it, it's acceptable. So whatever bulk theory fields that you have in the system, then you compute this and you find this entanglement entropy. This is the claim. Okay, so I think I said various things. X is codimension 1. Sorry, X is codimension 2. Sigma X is, well, let me just write it as d of sigma X is X minus A. Yes, bulk field dx is the von Neumann entropy of the bulk EFT field on sigma X. That's just a formal way of saying that this is, that's essentially the homology is, it's essentially, you define it using a vector space structure. So there is a natural notion of subtraction. So this can be, X minus A. I don't want to get into it. It's like another, this is just basically a statement that this region is contained between this and this. So if you have 2 points, homology is usually defined by starting with simplices and so on. So if a simplex, if you have a point, this is the smallest one, so to speak, and this is a one-dimensional one. So if I think of this as some length, or some set which is this, then this is, and this is my, one boundary is, let me call it B1 and B2. Then the natural way in which you define homology is via this. So it's roughly something like that. It doesn't really, this is, you can think of it as whatever intuitively you think of it is correct. So, so that's the definition of, bulk, from the bulk of this quantum extremal surface. So what we want to do today is we want to kind of think of this calculation as being a calculation. So far this is a solid territory. Okay. So the rest of the things that we are going to talk today are not really solid territory, or solid in the sense, I mean, assuming that we can calculate this thing, which is, as I said, almost never the case. So
why is it so hard to calculate the
essentially because in general, see, I mean, if you, so entanglement entropy, let's say you want to compute entanglement entropy of a, for instance, if you have Yang-Mills theory or something like that, we don't even know, I mean, it's essentially the problem of most quantum field theories are strongly coupled or etc., etc. That's already one problem. You know what I'm saying? Like, so for instance, if you look at the calculation of Srednicki, he makes the assumption that these things, quantum fields, free fields, can be approximated by like spring-like objects like you have in the beginnings of all quantum field theory books. That's his regulator. So then he computes that, and and then he does some calculation, okay, some result. So it depends on, so there are various reasons. So first of all, this object by itself is, one reason why it is not that well defined is because you need to introduce the epsilon UV. That's actually a good point that you mentioned it. So the epsilon UV is some bulk effective field theory cutoff. Okay, and this bulk effective field theory cutoff, so let me digress and then I'll come back and answer your question. So in order to define this object, you need to have an epsilon UV, which is, as I said last time, it's an object that you need to introduce in your bulk effective field theory. But note that epsilon UV is, in this length scale, is always much higher than L Planck. Okay, so this is always going to be a smaller correction compared to this. Bulk effective field theory cutoff is always assumed to be lower than the Planck scale. Okay, so this is something important to remember. So because of which this guarantees that this correction is roughly speaking small. Okay, so so this is at least we will soon actually see that that is not the case though. So this correction, that's one reason why people did not take this very seriously for a long time. But so the reason why, eventually we will, so it turns out that if you wait long enough, okay, so I'll explain why exactly. There is a parametric sense in this which quantity can actually compensate for the largeness of this. Okay, so like the quantity that you're getting here, let's say you're computing some object. So this may not seem like, this if it is perturbative in G Newton, why is it that this quantity can correct it? Right, so that's a question you might ask, and that question I will not fully answer today. But this is the reason why people did not calculate it for a very long time. Okay, so the point is that you might think that G Newton is very large. This is not going to correct it, so why care? Right? But what happens is that if you wait long enough, if there is enough Hawking radiation has left the system, the accumulated entanglement entropy of this thing over a very long time can be very high. Okay, so if you just had, so this it's I like to think of it as a parametric dependence. You can also argue for it in terms of a certain divergence that comes up in small, when you compute the entanglement entropy in radial direction. So this is, so that is going to take us in a digression in some other direction. So I'll just mention, there is the paper where Pennington, I think I forget the number, but it is in, it has, the first word is entanglement wedge. So you can look at how he calculates it, including one of the appendices, and you will see that there is a divergence that shows up here, which he uses to compensate with the 1 by Gn. That's the way in which he actually does it. But one way to think about it, as you will see, is that if you wait long enough in Hawking radiation, there is after the page time, there is enough modes in the sink that the entanglement between the interior and the sink is macroscopically large. So it is in some sense a parametrically late time type of calculation. Okay, so I'll say that when I get there. So my point here was that this is the reason why people have not really thought of doing this before, even though this quantum extremal surface was there actually a few years before the actual calculation was done. Okay, so the idea that this is the natural quantum extremal surface object one should compute instead of the Ryuta-Kenagi thing was known for a bit. So now, so let me answer your question. What was your question?
So
why is it not what?
Why is it hard to find entanglement law?
Yeah, so that answer is kind of basically what I said, which is that field theories are generally speaking, we don't know how exactly their entanglement structure works, right? So computing anything is hard. That's one answer. Then there is this fact that you have to introduce a cutoff, which is sort of an ad hoc quantity. And then there is the third, but of course, that's what I mentioned yesterday, that if you add this 1 by 4 G Newton, that epsilon UV basically is essentially a correction to the G Newton. You see, so that's one way to kind of justify the fact that this object overall is a better defined thing than either of these quantities. Okay, so the answer to your question is basically just that quantum field theory is hard. So it is, one reason. It's like in 2D conformal field theories, using indirect methods you can calculate it. But in general, in strongly coupled theories, we don't know how to compute most things, right? So you can do various things in perturbation theory, which is what the calculation using free field approximation means. Okay, but in many cases when the theory is like strongly coupled, etc., this is not a calculable object.
But when like black hole is like evaporating, the outside radiation like we can approximate like using photons.
Yeah, that's what we will do. That's what we'll do. So, but I'm saying that, like, many cases you would really like to compute this, in an interacting theory, or worry about various details that are there in the system, right? And many of those things, I don't think they are really studied in a systematic way. So also another thing is that you need to also check this systematically against CFT calculations. That's also hard. Because on the CFT side, the entanglement entropy in 2D CFT, we know how to compute it, but that's really all we know. Okay, so that's, let's say, another sort of. Yeah, so once you, so what you do is that you take this quantity, you extremize it and minimize it and determine this x, and that's your quantum extremal surface. And the claim is that the entanglement entropy of this quantity is computed by this area, this entire thing of the minimal guy, and whatever is in this region is basically reconstructible from the boundary region A. This is the claim. Reconstructible. I mean, I haven't really talked about reconstruction, so that's a different direction. So, any other questions? I mean, okay, so now we are really like, so this is a whole story there. So let me not get too distracted. Okay, so this is if you know your field theory operators living in the causal diamond associated to this A, then you can construct all the things within this region. It basically sort of the entanglement wedge sigma x is the entanglement wedge is basically how to construct it is basically by shooting light rays. There are various levels at which you can do this. So for instance, if you're looking just at Ryuta-Kenagi surfaces, you have some boundary subregion, so this will correspond to a boundary causal diamond, and then you will have a bulk causal diamond like this, and at the classical level, that's the entanglement wedge. Okay, so yeah, so the reconstruction of the full quantum entanglement is a whole, another story, and I don't think it is fully operationally how to do it is. I don't think it is still completely understood, but it could be my ignorance. Any other question?
So what if we calculate Hesburg field? The black hole just form, so that will be 0.
It will be 0, yeah. I mean, if
then this form of.
Sorry.
People verified this when that term is 0.
When this guy is 0.
No, the Hesburg.
Yeah, that we will talk about now in a minute. So yeah, so the calculation that we are going to do is basically going to look at this guy throughout the entire history of the black hole. So, well, I mean, we are not going to do the calculation, but I'll tell you what happens. It's kind of straightforward. Like the qualitative picture is quite straightforward. Okay. Any other questions? I think I have gotten this in various directions. So we are still where we started, more or less. But any other questions? Let me just finish off questions once and for all, and then we'll go. Okay, so if there's no question, so yeah, so the thing I was saying was that at least at the very basic sort of the pictorial level, not pictorial level, so this is supposed to be a perfectly well-defined quantity in the CFT, right? If you could calculate this, then this is that. Of course, I forgot to say one more thing, which is that there are in principle corrections to this coming from the fact that you might not always be working with, bulk effective field theory. You can introduce higher derivative corrections. So which means the area, the area of the entropy is not just the area of the surface, but it could also contain like, other higher curvature terms which are integrated on that surface. Okay, so that means that this guy, so this is sometimes called walled entropy. So if you have higher entropy, higher order terms, then that is the actual entropy or the area that, there is a correction to the area coming from higher derivative corrections. So that's what this guy is. So here I'm talking about G Newton corrections. Here I'm talking about higher derivative corrections. Okay. So but the point about these guys is that these are all local functionals basically on the surface. So you can just integrate them, and it's in some sense it's just that your definition of area has changed. That's all it is really doing. So in that sense, it's not a very, it's not a particularly, it's not a conceptually that much tricky thing. But this is, I would say, more somehow tricky because we are working with G Newton corrections. Okay, and also the question, it's all orders in G Newton, but not at finite n. So this is the final thing. So, okay, so now what do we want to do? We want to basically take this system and couple it to a bath, because if you take a large black hole in ADS, it's not going to evaporate, as I said, right? So the general picture is that, so we consider a system which is H total, which is H CFT tensor sum H sink. Okay, so now you are evaporating your system. You could phrase this calculation and in the language of flat space also by putting cutoffs and all that, and it's believed to be correct there as well. But let's try to do it in this language at least first. And what you do is you start with a state. So you're looking at some black hole state at various epochs. So initially you had a black hole that formed by collapse, then you wait long enough, and then finally it gets to space-time, and after that. So what happens is the question. Okay? So the idea is that this state, when you initially start, you're starting with a freshly collapsed black hole, let's say, constructed in the CFT, then you couple it to a sink, and there is hardly any radiation that has left the system. So that is your initial state. And then when you wait long enough, we are interested in computing the entanglement entropies associated with this density matrix and this density matrix. So the sink you can think of as some infinite system. So let me draw a picture here. So this is your this is your black hole, and radiation is leaving the system, and this is the boundary of ADS. This is a non-gravitating space-time that you're attaching to your ADS, if you like to think of it that way. Okay? So all of these things, one can ask many questions, but yeah, so let me just go ahead with what people say. Okay? So this is so then the radiation leaves the system, and this is basically a sink. Note that there is infinite volume here. This is not a system that is in equilibrium with this. This is a sink. Okay? So it just evolves. And because of the fact that you are starting with a pure state and it stays a pure state, we expect that the entanglement entropy of this CFT state, the CFT, rho CFT, is going to be the same thing as S of radiation. So this follows from the purity of the total state. Okay? So our goal is basically to compute the entanglement entropy curves of either of these entanglement entropies. This is what we want to do. Sorry? The sink is imaginary. Sink is, you can think of it as an excuse for a black hole in flat space, and you're thinking of the ADS boundary as an analog of some kind of a cutoff within which you're putting it. Even though there are some conceptual differences, that's largely correct. Okay, so this is at least what people expect. So the sink is imaginary in the sense, it's essentially just means that you're coupling the CFT to some other system, which is a huge Hilbert space into which the radiation is going. It's essentially a boundary condition for the radiation to leave. That's it. So whenever you add a boundary condition, that's what you're really doing. So if you have, let's say, if you say that if you have a non-reflective boundary condition or a transmitting boundary condition, what you're essentially doing is you're introducing a certain kind of coupling to your, Hilbert space between this and this. And the coupling is a certain preferred kind of coupling, which largely we would like to be agnostic about. So in some sense, the question is whether, such couplings exist. And generally, we believe that they exist. So which is the reason why leaky systems happen. So if you evolve this whole thing, essentially what happens is the modes of this thing will flow into the other one and just keep going. This is what we are hoping. Okay? Any other questions? Those questions are reasonable. But essentially what we mean by that, there is a lot of phase space into which the radiation is lost. That's what we really mean. Any other questions? Okay. So, right. So what we expect from this kind of a picture, our favorite picture, is that something like this will happen, right? So this is the page curve, and we want to reproduce it using. So of course, if you assume that it is a pure state, we can of course, we must have it come back. But now what we are doing is we are actually going to use bulk effective field theory. Okay, and from there we are going to try and reproduce it. So the idea is that instead of working, so what Hawking did in his calculation was essentially just keep track of the S bulk piece in this entanglement entropy. Okay, so his assumption, if you assume that the state is under root state, etc., his calculation essentially amounts to the statement that this quantity is S bulk, and that S bulk keeps increasing is what he finds. And now we are saying that our prescription for the pure state entropy, so we have a magical prescription for computing the left hand side, and that is basically to do this prescription, and then we follow that curve and then follow that quantity, and then we find that it turns around. So this is what we want to do. It's fine even if it is gravitating. So it is just that in ADS-CFT, so we are not coupling it to as long as this radiation is sufficiently, dilute so that it doesn't back react, whether it gravitates or not is not very important. In fact, that's why people think that this is the same thing as in flat space, right? So in fact, if you look at Maldasena's review, which I mentioned last time, he basically does this calculation in flat space with a cutoff. So this is. This is the way in which Pennington did it. So, in fact, with the cutoff I have a paper before Maldacena where we do the exact same thing. So, yeah, so that's so with the cutoff or without the cutoff, it doesn't really matter. So, it's generally, the rough idea is that the graviton, not the graviton so much, the radiation, so the degrees of freedom are sufficiently diffuse that they don't back react sufficiently. Then there is some sense in which you can, but the precise sense in which it can be done has still not been clarified. I should also say that. Okay, so there is a sense in which this can be treated as a non-gravitating bath. Okay, so this is the essential difference. So I'm doing this calculation in the language when Pennington did it, but in Maldasena's review, for instance, he puts a cutoff there instead of the ADS boundary. Okay, so note that, so one could criticize both approaches. One of them you could say that, okay, there is, this is ADS and there is just empty space sitting there. How much of a model is it for black hole entropy? You could argue this kind of questions. And I don't think any of them have been sufficiently cleanly resolved. Okay, so, and I think that.
What is the gravitational dual in this scene?
There is no need to have a dual, right? Why do we have to have a dual for this? There is no gravity here.
But if it is in the boundary, then we should also have.
It is not in the boundary. It is a system that is, so the boundary is the CFT and you're coupling a sink to the CFT. That's the picture. Okay? So you have a CFT, so if you want, the dual would be basically this with some, sometimes people draw this picture of a quantum dot coupled to a quantum wire. So this is basically the analog of the CFT and this is some big system to which things are leaving. Okay? Any other questions? So yeah, so the nature of, the way I'm doing it, basically this calculation is in the way in which Pennington and Engelhardt, etc., have done, which is to couple the ADS system to a bath and then let the radiation go. That's it. So, the sink doesn't have what? See, this is null infinity, right? This is infinity. So basically, this is an infinite distance away. So you don't need to, maybe you'll have to specify. See, also note that this is not gravitating. So you don't even really have to specify what the boundary conditions are, other than to say that here there is an open boundary condition for things to leave. And once it goes there, because there is so much infinite phase space here, it's never going to come back. So, but all of these are details. I don't think that, people believe these things. I don't think it is. But they're not, I don't think they're bad assumptions. They're good assumptions, and that's the kind of assumptions that you have to do if you want to solve a complicated problem. So getting lost in technicalities is different from, making the correct assumption. You know what I'm saying? So I think these are fair assumptions. So if you, so the key point I'm trying to make is that, it's essentially a boundary condition for the radiation to leave the system. And the point is that once you make the assumption that the Hilbert space is large, once this thing leaves the system, it's never going to come back. You don't have to worry about it.
Just want to get rid of it.
Exactly. So it's a model for what happens for black holes in flat space, right? Because the radiation that comes out of the black hole, it just leaves the system and it goes on forever. So that's the infinite phase space at the boundary of flat space. So that's what that is.
So, but calculating as well, so we take it to this radiation.
Computing S bulk, yes. Yes. We will take it into account. Yeah, we'll take account all the things, I mean, to the best of our ability. Yeah. So, yeah, since, you know, so I will make you a little bit more uncomfortable by saying that the place where this calculation, I would say, is most legitimately done is in 1 + 1 dimensions. Okay, and 1 + 1 dimensions, I mean, one could criticize various things about gravity. Like gravity is kind of trivial in 1 + 1 dimensions in various ways. So you might say that that's a big problem, but I still don't think it's a problem. So for instance, I think, you know, so the reason is Hawking radiation is a one-dimensional problem. You know, zero, you know, essentially it's a spherical, you know, most of the Hawking radiation comes out in zero, you know, L = 0 modes. So I don't think it matters. So, but there are people who are upset by this various, you know, everybody is upset about everything. So it's like, so yeah, I mean, I know, for instance, that Mathur is not happy with this, but the video is there, so I'll not make more comments. So,
all the things that you are writing here, it is true in the larger limit.
So, I mean, okay, so none of these things, I'm not really talking directly about, see, this is a bulk effective field theory calculation. Right? So, it is in some sense in the strict, you know, in the large n limit. But I am keeping track of this 1/g Newton thing plus all order corrections. Okay? So, this is, large n means, yeah, so it is large n, but I mean, you know, we are, so yeah, so this is kind of related to the question of how should one make this large n approximation, and what is the what is the way in which we should take the large n limit for various correlation functions and so on and so forth. Okay, so that's a somewhat tricky question. I don't think that also has been adequately addressed, but I think that you will see that this calculation is reasonable. So essentially what we are doing is that we are waiting long enough and then computing this quantity, and then we see that there is a flip in this, you know, which term in the quantum extremal surface calculation dominates. So, and yeah, so, and as a result, we, you know, this page curve comes back down. So how exactly one should take the large n limit here is actually, I don't think, I legitimately think it's not known. You know, I think that part of the reason is these are not typical states. Okay, so as I said, evaporating black hole is not a typical state. So it's not clear whether you need exponential precision to make this calculation legitimate. You know what I think? You may not need that. So if you are working with the typical black, you know, so the eternal black hole in ADS at very late times, then you will have to worry about exponential precision. So here it is not clear whether exponential precision is required. Okay, so but it certainly is the case that I think it will be nice to kind of you know, at least have a toy model where some of these things are cleanly ironed out. But so some of the legitimacy of the calculation actually comes from the fact that this is a natural thing. So people had introduced this quantum extremal surface for other reasons. Okay, so it is not as a you know, as a tool for getting this that they had introduced it, and that matters. The chronology of the events matters. So it was introduced first for computing other things for other physical reasons, and as you know, as the correct version of the Ryu-Takenagi formula. That's how it was really, you know, it had a, you know, Ryu-Takenagi had a fairly long, in the sense, a decade worth of history, in which initially it was just area minimization on some t = 0 slice and so on and so forth, and gradually it became like this full-fledged expression, which is this quantum extremal surface formula, and that quantity was there for other reasons, and then people applied it to this, and then they found that it worked. So, and that matters. You know, I think it is like the way in which, so if we had just introduced it so that you could get back this thing, then many other things I think would have been worrisome. But now I think the real question is, why is it working? Rather than, you know, because it is, rather than like trying to figure out where it is, you know, trying to find out loopholes why you should not trust the calculation is not the right approach, in my opinion. The right approach is basically to look at the calculation and, you know, because it is working for whatever reason, why is it working is a real question. You know, since there are so many questions about it, and this is, you know, couple of years ago, this was kind of a mini, let's say, revolution in whatever is string theory now. So and so that's why I thought, since you have many questions, and I think many of them are good questions, but I think that still, I think the calculation stays. So that's all. So yeah, so I think the question that you asked, I think, is probably the kind of the most interesting question in some sense, which is that why exactly? So how should you, do you need exponential precision in order to make this calculation work in n? That I don't think that is the case, precisely because of the fact that evaporating black holes are not exponentially, resolved entities. Because evaporating black holes are, they are not typical in the microcanonical ensemble at all. So I think that, yeah, so that's one comment. Any other questions? So, yeah. So now what we are going to do is so now we want to compute this, right? So, so you can look at my paper. I have kind of forgotten the logic a little bit here. So, so let me just give you so there is a summary that I put for my own benefit later, which I will refer you to. So it's kind of a review of, so section 4.1. So you can go and read it. So it's formulated in the kind of a flat space kind of language, but it's really the same thing. Okay? So, yeah. So what are we doing? So we are basically starting with a state which is a freshly collapsed black hole where there is no radiation in the sink. That's where we are starting. Okay? So, and we want to compute, one more comment before we get into it, which is that we are going to compute this entanglement entropy for the entire boundary, the CFT. Because we are interested not in some entanglement entropy of some subregion or something, we are interested in the whole system, right? We want to see the black hole as a system living in the CFT and it evaporating somewhere else. So that's what we are interested in. So that makes our calculation somewhat simpler. So the idea is you start with this collapsed state and it is pure, and in the initial time there is hardly any entanglement between the radiation. I mean, there is no radiation has left the system. So let me just draw this as so let me just repeat that picture here. So hardly any radiation is in the sink, which means that when you compute your entanglement entropy, so one more thing I forgot to mention. So let me just, so I want to mention something called entanglement wedge complementarity. It's a very simple fact, so we can just mention that, and this is also part of the assumption, even though there are papers by Busso which claim to derive it. Okay, so entanglement complementarity is, so let's say that you have, let's look at a cross section of the CFT. There is a black hole sitting here, or this is the QES. So QES, this is the boundary, and outside here there's some sink. Okay, so if you compute the QES, the claim is that everything between the QES and the boundary is in the entanglement edge of the CFT. So CFT is sitting at the boundary, right? And everything else is the sink outside. Okay, so the entanglement edge of the CFT is basically everything that lives here. Okay, and the claim of entanglement complementarity is that whatever is not inside the QES, I mean within the QES and the boundary of the ADS, which is basically this region, is in the entanglement of the radiation. Okay, so it's a plausible assumption, and there are, under various assumptions, you can prove versions of this. So this is something that we'll also believe. Okay, this is a statement that is also assumed in this paper of Pennington. And so these are the two papers that did this, which was Almairi, Engelhardt, Marolf, and Maxfield. Okay, so these are the two papers which are roughly, the first one is roughly what I'm kind of following, if you like. Okay, so where are we? So, yeah, so now the point is, so if you are looking at, you want to compute the entanglement entropy of the radiation. That's what we want to do, right? And the radiation, so what is the argument? Yeah, so we have S gen, the prescription is S gen is given by A by 4G plus S bulk. Okay, S bulk is what we call the radiation. So S bulk is essentially defined as the black hole, the black hole is radiating out. There is some initial ingoing states which are there inside the bulk are getting entangled with the radiation that leaves the system as time goes on. So the entanglement between the interior and the sink is increasing with time. So that's the first observation. Okay, and that's really what S bulk is calculating. Okay? So the point is, in the beginning, because there is hardly any entanglement at all between, hardly any radiation has left to the system, right? So which means that if you are trying to minimize this, so the way you compute the quantum extremal surfaces, you place some surface somewhere, anywhere on this Cauchy slice, let's say, at some particular time, and then so this is my ADS, this is my singularity, so this is the center of ADS, okay? So this is not an eternal black hole. There is a black hole that is formed by collapse in ADS. Okay, so this is basically like the center of ADS, if you like. So, so this is analogous to the center of it's like the R equal to 0 location of the flat space. That's what it is. So anyway, so this is my location for the quantum extremal surface. Potential quantum extremal surface, and the claim is that, let's say that, because there is hardly any contribution coming from this in early times, right? S bulk is essentially 0. So which means that you are going to minimize this by minimizing the area of this surface. So this thing should be 0 size, okay, which corresponds to this QES being here. Does that make sense? It's a trivial statement. So there is no contribution coming from S bulk, which is the radiation due to the entanglement between the interior and the sink. Okay, so and that is 0 at early times. So which means that you are going to minimize your S gen by going to the center of this thing, so that the entire spatial slice is in the entanglement wedge of the CFT. Any problems? It's all good? Yeah, so that's essentially what it means is that there is no entanglement between the radiation inside the black hole and the sink here. So you get the maximum amount of, you get the minimal quantum extremal surface by minimizing this radius. And if you minimize the radius, this is essentially 0. Right? So, and slowly, but initially it was 0, so you start somewhere, let's say 0 here, okay, some approximate 0, and then slowly, as the radiation is leaving the system, you start moving up, just like in the case of the Page curve, right? Because slowly this system is, as the radiation is leaving and going into the sink, the entanglement is increasing. So S bulk is slowly going to increase as the black hole is emitting radiation, right? So this is the first observation, and the second observation, and this is the part where the calculations are actually explicitly done, is that essentially immediately after the formation of the black hole, and roughly speaking a scrambling time after the black hole is formed, if you minimize this quantity, and that minimization is where some technical tools are required. So one of the ways in which people have done this is in using 2D CFT methods, which is in this context of this JT gravity kind of thing. Oh, I erased it. So this is JT gravity plus JT gravity is a two-dimensional theory plus CFT. This is the context in which these guys did the calculation. Okay, so there the calculation is totally doable, or at least systematically doable. But the problem is that it's a 1 + 1 dimensional system. So there have been criticisms about whether it is really reliable as a calculation. As I said, I think it is. So, and this is the first setting, and the second calculation of Pennington is more heuristic in many ways, but it is done in higher dimensions. Okay. Higher D. So, but the key claim of both of these calculations, which is something that we'll take as a black box, is that there are two QESs that appear after essentially a scrambling time after the black hole is formed and starts evaporating. Okay, and one of them is close to the horizon in the interior, and the other is basically the one that I already drew. Okay, so there is one here and one here. Basically a geometric calculation and some information about the entanglement entropy of the CFT entanglement entropy of the bulk fields go into this thing. And there are, by assuming, like he was asking, by free field theories and so on, you can make estimates for it. Okay, and using that, we can compute that there are two quantum extremal surfaces that show up. For once a black hole starts evaporating, there are two. Okay, so this is in some sense sort of the technical observation, but the key point for us is that if you have two quantum extremal surfaces, which one should we pick? We should pick the one that minimizes the generalized entropy. But as long as this S bulk is sufficiently small, right? As long as the S bulk is sufficiently small, you are always going to stay here, right? Because if it is small, you have only two extremal surfaces. So you either pick one or you pick this one. If you pick this one, you're keeping a lot of the area. This is, especially late, close to the spacetime, etc. So this thing gets closer and closer to the horizon from the inside. Okay, so which means that the area of this is essentially the area of the black hole. Okay, so if you keep this quantum extremal surface, you're counting the area of the black hole worth of entropy, and area of so this will be bigger basically. So what it means is that as long as the entropy in the S bulk is smaller than that of this guy, right, it is better for you to stay here, right? And in which case your S gen is contributed by this, and it'll keep rising. Okay, so that's the first half of the page curve. Okay. I didn't tell you. So this is the calculation in those two papers, and I recommend maybe this one. I think this is more a controlled calculation, I would say. This is, but there are some interesting thoughts in here also. Oh yeah, that's a good question. So it is not the same CFT as the dual. So this is a 1 + 1 dimensional calculation where the JT gravity is coupled to a CFT in the bulk. So yeah, so there are, if you ask more questions, I will probably confuse you more. But unfortunately, yeah, so this calculation becomes doable in a certain, so the dual of this doesn't really matter for this calculation. This is entirely a bulk calculation where we are in, so we just need to know that there is a CFT. Right? There is a bulk calculation and a bulk prescription for calculating some boundary object, and the boundary object is just some entanglement entropy. So we don't really care what the dual theory is, right? That's exactly the statement, yeah. So the QES is a bulk thing, and it's two locations in the bulk. Fine?
So are they identified like the same thing?
No, they are completely different. In fact, that's the point. Because if you're see, the point is that different QES. So there is. This is the second time in a row. Well done. So So the point is that S gen, right? You're computing this S gen of this quantity, and this. The prescription is that you have some A of chi and then some S bulk corresponding to that. You add these two things, and then you find the one that is the smallest. So if there is a surface, if there are two surfaces which are both local extrema of under variations of this chi, you pick the global minimum. And that's what these two are, essentially extrema of this guy, and that's what it means by quantum extremal surface. But then this is the minimum at early parts of the page curve, and later on, I'll argue now that this is the minimum. Is that first part clear? So because this is, there is not, if you put this guy in, so let's say that at the early parts this S bulk is small. Okay, this is very small. So if you just keep this, you're just unnecessarily increasing your S gen, right? So you don't want to do that. So you want to look at the smaller one which is sitting here, so that all the contribution is coming from this guy. Fine? So I don't want to waste this chalk. Let me just put it back. Okay, so now we want to look at the part of the curve which comes after the page time. Okay, so page time is basically defined as these two things becoming comparable, right? So so what that means is that after the page time, now it benefits this minimization process if you work with the guy which is close to the horizon. Right? Because now the contribution coming from this guy is smaller, because this is much larger, because you're going higher and higher and higher. Right? So yeah, so there is one more little assumption that is going in here, that I am assuming that my S bulk here, which is, it's the I'll address that if anybody asks that. Otherwise, I'll just confuse you for now. Okay, I'll say that at the end. So there is a sense in which this S bulk I have not resolved whether it is a fine-grained S bulk or a or a thermodynamic S bulk. I've not really done that, but ask me at the end and I'll say some words which may not be fully satisfactory. So, but the point is, if this is the thermal entropy that is going up, and the page time is really defined as an equality of the two thermal entropies. Okay, so this S bulk, as it goes up and it gets over to the page time, you basically find that now this is the higher guy, and you work with this second A chi, and so now your quantum extremal surface shifts at this point, somewhere around this point, and now you are in the, now your S gen is controlled by this guy and not this guy. And because it is controlled by A chi, as the black hole evaporates and becomes smaller and smaller, it will fall into the same curve as here. Is that okay? So I mean the story is, so the only part where you have to believe me is that there exist two quantum extremal surfaces which you can do at varying levels of solidity, let's say. And but actually there is even better calculation, I would say, which also I cannot tell you in real time, but the even better calculation which is sort of doubly holographic, where you compute an RT surface. Here in some of these calculations it is, somehow, because the system is 1 plus 1 dimensional, etc., the calculation is very clean, but one would like to have more familiar examples, or more a higher dimensional example where there is genuine structure in the RT surface and so on. Here basically, for instance, it is just in 1 plus 1 is just a point, right? And JT gravity, the area term comes from basically the value of a scalar field. It's not quite the area by 4G form that typically we have in higher dimensions, etc., because it's a point, right? In 1 plus 1 dimensions you have to explain what the Hawking entropy is, and it comes from the certain value of a scalar and so on. So all of those things, in my opinion, are legitimate, but at the same time, there have been calculations which are done after that, which really do this in a sort of what is called a doubly holographic setting, where you really can see the phase transitions in some geometric RT surfaces. So what you're really doing is that instead of looking at, so this entire thing can be understood in terms of some higher dimensional RT surfaces which undergo switches between, there are two different kinds of RT surfaces. So you can, that's one way in which it can be made a little bit more, in some sense better than, it came after these calculations, so in some sense these guys get the credit, and I think it is important, but there are calculations in doubly holographic settings where you can really see this phase transition. And because it's a geometric phase transition, somehow it's a bit more compelling, I would say. Here, because it is a little bit, it's a trade-off between an area term and bulk entanglement entropy, so you might think that this is almost guaranteed to work in some sense, so because it's essentially coming from the fact, so the existence of this the non-trivial observation here is that there exists one more guy here. So that's the thing. So that was true already in those calculations. So, but if you are not convinced by that, there exist versions of this calculation which are done in this so-called doubly holographic settings, where you can really see the phase transition between two RT surfaces, which are a proxy for this generalized entropy phase transition. Okay, so let me just finish one second. So, but I also want to add a caveat that when you are working with these doubly holographic settings, there also are other issues related to the fact that now you're not just working with the usual holography, but you are working with a hologram for a system that involves gravity. So there are other issues of that kind. But yeah, so there is, I'm stating something and also destroying it at the same time during this entire talk. So, but yeah. Anyway, go ahead. What is your question?
I was asking, after the patent, the second QES has the lesser generalized entropy. That's why we're choosing that.
Yeah, and the reason is sort of straightforward, right? So the point is that if your entanglement, if your QES is here, what it really means is that, so if the QES is here, what you're really saying is that, if your QES is here, all these guys which were entangled with all these guys are no longer being counted for the entanglement entropy, right? So so what is the structure of entanglement? The entanglement is basically that the interior modes are getting entangled to the radiation that is leaving the system, right? So there is some entanglement entropy that is building up. So But the claim is that once you are past the page time, if you jump to this QES, whatever is, so now what that means is that the QES is sitting here somewhere. So this is the horizon, and let's say this is the horizon and this is the QES. So most of the interior is no longer in the entanglement edge of the CFT, which means by this entanglement edge complementarity that all of this is lying in the entanglement edge of the radiation. So if both this guy and this guy are in the entanglement of the radiation, that means that, you know, it has essentially purified the system, right? If this was, you know, if you have an entangled state and you split it, one piece which is on this side, one piece on this side, then you will get entanglement entropy. But if it's a pure state, then you're not going to get an entanglement entropy. So whatever was, there was a lot of entanglement between this guy and this guy, but by jumping to this QES, you're essentially saying that this is in the, this and this are basically now counted as the same system. Right? So because of which there is no entanglement, you know, so this whole thing is gone, right? So this was contributing to the entanglement because this was being counted as part of the CFT system. So this was like really contributing to that here, but now that you increased it to this, all of this is now here, and this is, you know, only the exterior of the black hole is in the CFT. Okay, so this is kind of like a very direct, so the fact that this geometric calculation is actually able to do this is sort of a piece of evidence for believing our old statement that the interior is actually the same thing as the radiation after page time, because that's literally what we are seeing here. Was that clear? Because, you know, it's a trivial idea, but I think when you say it, it always seems more complicated than it is.
Sgen of QES2 will be less than QES1 if you calculate it.
Correct. Yeah. So the point is that before page time, Sgen of this QES is the one that is smaller, but after page time, Sgen of this QES is the one that is smaller. So and this guy in the first half of the page curve, this guy is increasing, and in the second half of the page curve, this guy is decreasing. So because its area of the black hole is going down with time. Okay, so yeah, so the non-trivial bit, the one, so this calculation is, the way I presented it almost sounds completely trivial. There is nothing going on, almost, right? But the reason why it is not completely trivial is because this QES need not have existed. That's the reason why it is non-trivial. You know what I'm saying? So otherwise, this is a geometric fact about late time black holes which have radiation inside them, or in the doubly holographic prescription, some RT surfaces in some higher dimensional geometry. Okay, so that's why this calculation has at least one non-trivial bit in it. Okay, so the fact that these non-trivial quantum extremal surfaces exist is what makes this a non-vacuous calculation. Otherwise, essentially, it's a declaration that, okay, at late times, the entanglement edges of the interior is in the radiation. You know, but here we have a geometric prescription. So this value, at least in many cases, one can calculate it. In the 2D CFT case, it's a completely legitimate calculation. Okay, so whether you want to believe that as a proof for all higher dimensional black holes is up to you. So, but but it's a completely legitimate calculation. In the higher dimensional case, it's less solid, but it's still not vacuous, and there exists, as I said, these doubly holographic brain world kind of arrangements where you can really see that there exist some RT surfaces which need not have existed do exist. So that's the reason why this is a non-trivial or calculation. So now essentially we have this is the QES prescription. So if you have any questions you can ask.
Don't say anything about the page and then because they will it's going to be surface.
What do you mean? Sorry?
Around the page and they both comparable. So which QES will be choosing that's not
you mean at the which is the precise time? Yeah, precise time. I mean, okay. I mean, it doesn't really matter, right? We are interested in reproducing the thing. I mean, of course, in the CFT case, it is very precise. In the CFT2 case, it's very precise calculation. You get some specific answer and you reproduce the phase curve. But in this higher dimensional case, I would say it's less precise. But it's still like, the point is there is a, so the key point is that the QES exists already in a scrambling time after the initial formation of the black hole. So, and you can argue for that using this maximum prescriptions and so on and so forth. There is a nice discussion of that in Pennington's paper. The intuition for that I think is more clear in Pennington's paper, but the calculation is more, sort of reliable in the Almairi paper. So yeah, so that's the statement. And did we have any more questions? I think we can stop here actually. So if you don't have any questions, but maybe I haven't addressed all the points. If you have any questions, just please go ahead and ask, because I kind of, because there are so many questions at the beginning, I kind of went in a direction which was different from what I was planning to go. So I don't know whether I said everything that I wanted to say. Yeah, go ahead.
In late times,
Yeah.
why is it S bulk small?
Why is?
S bulk small at late times.
What do you mean?
Shouldn't the entanglement entropy of the radiation?
S bulk is big at late times, right? That's the problem. Because it's the reason, that's the reason why, because S bulk is big is why we are keeping this guy. Right? So the point is that, there is a contribution coming from the radiation which keeps on rising. And there is a contribution coming from the area which also keeps on decreasing. Okay? Here I am writing down the area of this extreme surface, let's say roughly. Okay, it's so but really in this picture usually people draw the area of the horizon, but it's roughly the same. So anyway, so the point is, like at early times this S bulk is small, and so because of which if you keep the extremal surface just close to the horizon, then you are going to get an S-gen which is very high, and you don't want that, right? So that's the reason why you take the other extremal surface which is close to or at the origin. So then after page time, S bulk is very large. It's bigger than A of a black hole, basically. That's the definition of page time, right? So this is much bigger. So which means that if you keep the minimal guy, which will count the S bulk, because if you keep the minimal, the minimal means the one at the origin. If you keep the QES at the origin, then you are going to keep S bulk. S bulk will be big. Right? Because what is really happening in some sense is that, so after the page time, so this is the sense in which I said before, there is a distinction between the thermal entropy and the fine-grained entropy of the radiation. Okay? That brings me, so I did not actually tell you what islands are yet. So let me tell you that after I say this. So here I have kind of phrased this sort of, I was kind of agnostic about, I was largely talking in the language of the entanglement wedge of the CFT. So, but now I can also talk about the entanglement of the radiation. So I'll come back to that in a second. So I'm just explaining what I already did to kind of, to address your question, which is that at late times, this S bulk is in principle very large if you keep the smaller QES. But if you do that, you're overcounting the S-gen, because the prescription is that you should compute the minimal guy. Okay? So which means that you should keep this guy which is near the horizon, in which case you don't count the S bulk, so that this is the correct entanglement entropy, or and then it can go down. Okay, so that's why I said that it is, it's always a little, there is some minimization, there is some to this thing, etc. But if you just walk through it, it's fine. I mean, it's just the same sort of thing. Yeah. So now let me say this fact that I mentioned about, So what we are really doing is, so this is something that was emphasized by Busso, which is that the S bulk, this statement that I made about the trade-off between S bulk and entropy, can really be only made if you're thinking of S bulk in terms of a thermal entropy, because it has to keep going up and up and up, right? So I will not resolve it, but I just wanted to point out to you. So there is, so I just thought I'll mention that. So this is, it's kind of an interesting thing, because it comes actually from the fact that you have to take it's indicative of some aspect of this which I have not yet mentioned, which is related to ensemble averaging and so on, which you may have heard at some point. So that's just to like kind of whet your appetite. But now let's come back to the islands. Okay? So islands basically just means that, so here my entanglement wedge was this region. So I'm looking at the CFT entanglement wedge, right? But now I could also look at the pure state of the radiation. I could compute. So the idea of Page's picture is that black hole is one system, or the CFT is one system, and the radiation is another system. So now if you are actually interested in computing the entanglement entropy of the radiation directly, both have the same Page curve, and they together share a pure state, which means that the natural prescription is that you should compute the complement of this region, which is this region and this region. Okay, so this is basically the radiation. This is the radiation Hilbert space, if you like. So the radiation Hilbert space has, in the after the page time, in the entanglement wedge of the radiation, there is a region in the interior of the black hole. So that's what this is showing you. Okay, so the radiation is, this is the radiation Hilbert space, where the radiation left. Okay, so and because by purity of the system, purity of the state, we expect that the whole system should be pure, right? So, and that means that entanglement wedge complementarity tells us that this and this are in the entanglement wedge of the radiation. Because the QES is still the same. Right? So, and this region is sometimes called island. That's all. It was already there in the first papers, but it was named, I think, later by Maldacena and company. So, yeah, I don't really consider it to be a different calculation. It's the same thing. If you just use purity and this, then it's kind of the same thing. Any other questions? Yes, please. Yeah, this region, yeah, so the picture that you can keep in mind is this one. Okay, so at any time, the cross section of the black hole, roughly speaking, looks like this. So this is the radiation. So this is the boundary of the, boundary CFT, if you like. So this circle, and this is the QES. QES is a little bit inside the horizon. Okay, the second QES. So there are two QESs, one corresponding to the center and one corresponding to a little bit inside the horizon. And the claim is that after the page time, this guy lies in the entanglement of the radiation Hilbert space. Yeah, exactly. Exactly. So, yeah, and sometimes people draw some wormholes and things like that there. Okay, so today's lecture and the next lecture, they are both supposed to be at a story level. So hopefully, but the story should be clear. So if it's not clear, you ask. Okay, so if there is no other question, I think that's a good place to stop.
Why was it called an island?
Let's why was it called an island? I mean, this is kind of like an island right in the middle. So, but what is surprising is in the first papers they did not call it an island. In fact, they didn't name it. So it was a naming opportunity that was sorely missed, I think. But anyway, yeah.